Hey guys, hope you are doing great. Today we're going to discuss about cardiac cycle and pressure volume relationships. As we know that heart has two basic functions. One, it acts as a pump that it pumps blood through the great vessels to the different parts of the bodies. Next, it generates electricity like AC node. That AC node acts as a pacemaker. Sometimes we lose the pumping function of the heart. For example, in heart failure, an AC node function or electrical function of the heart is good. But sometimes we lose the electrical function of the heart, but the pumping function of the heart is good. For example, in sinus arrest. Okay, so we discussed the electrical portion of the heart and the electrical functions of the heart under the title of rhythmical excitation of the heart. And today we're going to discuss the pumping function of the heart under the title of cardiac cycle. Okay, we will define cardiac cycle. Okay, what do I mean by cardiac cycle? For example, when heart pumps blood to the body, okay, so it produces a beat. This is called heartbeat. So one heartbeat is made of two parts. We will talk about it. The contraction part is called systole and the relaxation part is called diastole. Okay, so now we have one systole plus one diastole. So both combination of one systole plus one diastole make one cardiac cycle. Okay, or one heartbeat. So all mechanical events during one systole plus during one diastole is called a cardiac cycle. We will talk about it. Okay, so during this lecture, first we will talk about cardiac performance parameters. Okay, for example, there are some parameters like cardiac output, end diastolic volume, end systolic volume, stroke volume, and so on. Then we will talk about the phases of cardiac cycle. What do I mean by cardiac cycle and how many phases it has? Then we will talk about pressure and volume relationships, okay, and some curves related to this concept. Then we will talk about cardiac work because cardiac work is so important. A cardiac work is directly proportional to the oxygen consumption and ADP consumption. Okay, we will talk about it, don't worry. Then we will talk about Laplace's law and Frank Stirling law, okay? And also, then we will talk about, for example, the regulation of cardiac pumping, okay, that how the works related to the cardiac pumping is regulated. And also then we will talk about some clinical points. Okay, so come here. First of all, first is first. Okay, for example, let me first tell you that what a systole is and what a diastole is. Okay, then we will talk about in diastolic volume, in systolic volume, stroke volume, ejection fraction, cardiac output, preload, afterload, venous return, cardiac work, Frank Stirling law, and Laplace's law. Okay, so first of all, what is systole? Listen me carefully. When heart contracts, okay, so this contraction phase of the heart is called systole. Okay, so systole means contraction of the heart. Okay, about the diastole. Now when heart contracts, it pumps blood to the different systems of the body. But when it relaxes, so it accumulates blood from the pulmonary system, it accumulates blood from the systemic uh, blood veins. So this relaxation of the heart is called diastole. Okay, so relaxation of the heart is called diastole. This is relaxation. Got it? Now, during, for example, when heart is going to systole, so all chambers do not go simultaneously to systole. First, atria go. Atria is the plural noun of atrium. Okay, so first atria, these two atria go to contraction, then these two ventricles go to contraction. Okay, then these two atria relax, and then these two ventricles relax. Got it? So that's why in one systole plus one diastole, a lot of different mechanical events occur. Okay, so all these mechanical events during one systole plus during one diastole, as a collectively, all these mechanical events are called cardiac cycle. So one cardiac cycle is equal to one heart beat. For example, my heart is beating around 72 times per minute. Okay, so it means that my heart is going around 72 times to cardiac cycle phases. Okay, or my heart is going through systole and diastole around 72 times per minute. Got it? So this is called one cardiac cycle. We will talk about them, don't worry. Now let me explain these parameters. Okay, first of all, end diastolic volume. What do I mean by end diastolic volume? Listen me carefully. For example, here now my heart is during diastole phase, during relaxation phase. So I have amount of blood inside these two chambers. Okay, now I'm at the end of relaxation. Till now I haven't entered to the systole phase. Okay, I'm at the end of diastole phase. So this, at the end of diastole, if I measure these volumes inside these two ventricles, these volumes are called end diastolic volume. It means amount of blood inside the ventricles during diastole at the end phase of diastole, and it is equal to, based on Guyton and Hall physiology, around 120 up to 130 mils. Got it? Now, end systolic volume. Now listen to me carefully. Now heart is contracting. Okay, so when it contracts, it pumps blood. When it contracts or it goes to systole phase, it pumps blood to the outside of the heart. Now I'm doing systole. Okay, but now systole is going to be finished. I'm at the end phase of systole, but till now the systole phase is haven't finished. Got it? But I'm at the end phase of systole. So at the end phase of systole, amount of blood which remains inside these two ventricles, this remaining part of the blood is called end systolic volume. Got it? Now first of all, let me explain you stroke volume, then I'll tell you how we can measure end systolic volume. About stroke volume, stroke means beat. Okay, one beat. So amount of blood which is ejected by the heart in one beat, this is called stroke volume. Okay, for example, during normal situation, heart ejects around 70 mLs blood in one beat. Got it? Now we can find end systolic volume easily. Okay, now end systolic volume is equal to stroke volume plus a stroke volume plus a, I'm talking about end systolic volume. Okay, no, it's equal to end diastolic volume minus stroke volume. For example, for example, I have 120 ml blood during end diastolic phase. Okay, so end diastolic volume is 120, stroke volume is 70, so it's equal to 50. So here end systolic volume is around 50 mLs. Okay, but how we can find end diastolic volume? It's so easy. Okay, now here it's equal to stroke volume plus end systolic volume. For example, stroke volume is 70 and systolic volume is 50. So this is equal to 120. Got it? So these were these values. Now, ejection fraction. Listen, be careful. This is a bit important. Amount of blood which is ejected by the heart in one beat. This is called stroke volume. Now, amount of blood which is ejected by the heart in one beat, it's also ejection fraction, but here's a big difference. This is the percentage of the blood, listen me carefully, percentage of the blood which is ejected in one heartbeat, percentage of which blood? Of end diastolic volume, of end diastolic volume. For example, listen me carefully, it shows me the efficacy of the heart, that how heart is working good. Okay, now listen me carefully. For example, I have 120 ml of blood which is end diastolic volume. Okay, now I pump around 80 ml, which is around normally at first around 70 ml of blood, which is called stroke volume. Got it? So this is stroke volume around 70 ml. But someone asks you that, my brother, I have here 120 ml of blood. Okay, how much percentage is ejected by the heart in one beat? Okay, for example, this is equal to divided stroke volume divided to end diastolic volume. For example, stroke volume is 70 ml, end diastolic volume is 120 ml. So 70 divided to 120 is equal to 0.58. Okay, and it's equal to around 60%, around 58 or 60%. Now listen me to another example, so easy. Okay, now for example, I have 120 ml blood. Okay, now this time this heart ejects around 80 ml blood. So this 80 ml is simply stroke volume. But when you want to find ejection fraction of this heart, you will divide stroke volume per 120 in diastolic volume. So here 80 divided per 120 is equal to 66, equal to 0.66, which is equal to 66%. So now tell me which heart is working good. This one is very good because it ejects 66% of blood in one beat. It gives me very good cardiac output. I'll talk about cardiac output. So this heart is very good. This heart is this excellent. This is good. Okay. For example, another heart. There is a heart. For example, a patient has heart failure. Okay. Now this patient ejects in one stroke volume. For example, it has 120 ml blood. Okay, it ejects around 50 mLs. This is called stroke volume. So 50 ml divides per 120, it's equal to around I don't know, it's equal to around 40% or more than 40%. So now here you can divide them. Okay, and now here this this heart is poor, this is good, this is excellent, because it's very important. Because now nowadays, when we want to find the degrees of heart failure, that patient is in which stage of heart failure, we use this ejection fraction. Okay, this heart is not good. Okay, so ejection fraction less than 50, the patient is entering to heart failure. It means heart cannot prepare its functions. Got it? So this was about the only difference between ejection fraction and stroke volume was that stroke volume only tells us that how much blood is ejected in one beat, but ejection fractions tells us that how much percentage of blood that how much percentage of end diastolic volume is ejected by the heart. Okay, because as much we remain a lot of blood to the backside or to the ventricles, the pressure, the tension increases on the walls of this heart that we will talk about them. So this is not good for me that we left a lot of blood into the ventricle. The heart is good, which ejects around 60% of end diastolic volume in one beat. Got it? This was about ejection fraction, about the cardiac output. Now, stroke volume is amount of blood which is ejected in one beat by the heart, but cardiac output is amount of blood which is ejected by the heart in 1 minute. Okay, so stroke volume, cardiac output is equal to heart rate times stroke volume. Very important. For example, if my heart is around 70 beats per minute, so stroke volume is around 70 mls. If you multiply them, you will take around 5 liter bloods in 1 minute. But when you increase this side, which is heart rate, so the cardiac output increases. If you increase this side, and this time also the cardiac output increases. Okay, so it is directly proportional to the heart rate times stroke volume. But listen to me carefully. If a heart rate exceeds above the normal physiological range, which is 3 times, okay, or more than 180 beats per minute, so now in this time cardiac output drops. Why? Listen to me carefully. For example, now heartbeat is around 300. So when heartbeat is around 300, it pumps like this. So it pumps very fastly, and it does not give enough time to the heart during diastole to collect blood. So when you can't collect blood, you cannot pump enough blood. That's why the cardiac output drops if heart rate goes above the normal. Got it? So this was about cardiac output. Let me explain you preload and afterload. Preload, very easy concept. Listen me carefully. For example, this is heart, and now heart is during relaxation or diastole phase. Okay, so during diastole phase, I collect a lot of blood to the ventricles. Okay, now this blood during diastole, it puts a bit pressure on the walls of ventricles. Okay, it puts load on the walls of ventricle. So this load on the walls of ventricle during diastole, this is called preload. We will talk about them later on, that they are so important. So now preload is directly proportional to end diastolic volume. As much you increase the end diastolic volume, the preload increases. Got it? About the afterload. Afterload means now heart is pumping blood to the systemic circulation. For example, here I have aorta, okay, and after aorta, this aorta, for example, it divides into different branches, small medium sized arteries, and then it divides into furthermore branches which are called arterioles, and arterioles are then divided into capillaries. Okay, now if I squeeze these arterioles, I tight these arterioles, okay, so here the pressure increases. Like when I have a pipe and water comes out from this pipe, okay, when I put pressure at the opening side of the pipe, okay, at the mouth of the pipe, so pressure increases to the back side where is the machine. Got it? So here, when you compress these arterioles, so heart needs to increase its pressure, okay, so you put furthermore load on this heart. So now during systole heart pumps against these resistance, against these compressions, okay, so this load which is put it on the myocardium, on the heart, during systole, this is called after load. So after load is directly proportional to total peripheral resistance. It means the all resistance and all arterioles of the blood, all of them as a combined, they put pressure on the heart during systole. So during systole, heart tries to increases its pressure to overcome these resistance. Got it? This is very important during uh, hypertension and during treatment of cardiac diseases like hypertension, heart failure, and so on. That's why these concepts and these parameters are so important. Got it? Now about venous return. Amount of blood which returns to the heart from systemic circulation through superior and inferior vena cava and through pulmonary circulation through pulmonary veins. This amount of blood is called a venous return. Got it? So now about cardiac work, Frank Sterling law and Laplace law we will talk later on. Okay. So now let's talk about the cardiac cycle. Okay, that what are the phases of cardiac cycle. Now let me explain cardiac cycle. First of all, that we explain a cardiac cycle. Okay, let me tell you conduct about something about conductive system. I talked in previous lecture that here in right atrium we have a node-like structure which is called SA node. Got it? And SA node acts as a pacemaker. It generates electricity to the heart. Got it? So now here if we have some pathways between two atria, or from the right atrium to the left atrium, which are called as a collectively interatrial pathways. Okay, and also if we have some types of conductive system or line like system from AC node up to AV node, which are called internodal pathways. Okay, then this heart, the atria and ventricles are separated from each other by a connective tissue which is called fibrous skeleton. So the only way to transfer the electricity from the atria to the ventricles is AV node. Got it? Then electricity comes here, and from the SA node, from the AV node, it comes to Purkinje system. From Purkinje system, for example, bundle of His. From bundle of His, right bundle branch, left bundle branch, and then it gives a lot of branches which are called Purkinje fibers. We have already talked about all of them in previous lecture. Got it? So now let's start from the point where AC node fires. Okay, and we will come back to that point again. Okay, so it means that I'm talking about only about one heartbeat. It means about one systole plus one diastole, about the systole of atria, about the systole of ventricles, about the diastole of atria, about the diastole of ventricles, and opening of these valves, all about them. Now come to the first phase. When AC node fires, so electricity enters through gap junctions to the atria, okay, to both atria. So this electricity, which is called action potential, causes these two atria to contract. Okay, so this phase is called atrial systole or atrial contraction phase. So the first phase of a heartbeat is atrial systole or atrial contraction. So during each phase, we look to atria, we look at two ventricles, and we look at great vessels or aorta. Okay, the changes in these parts. Now, in atrial contraction phase, listen me carefully. Now, when these two atria contract, okay, they pump blood to the ventricles. Okay, now listen me carefully. These two valves, which are called AV valves, atrioventricular valves, and they are mitral in left side and tricuspid in right side. Okay, they are already open. Okay, before we enter to the atrial systole, I'll tell you that in which phase they were opened. Okay, now, so in this phase, in atrial systole, in atrial contraction phase, first atria pumps these two atria pump blood to the ventricles. An amount of blood which is pumped during atrial contraction phase, it's only about 20 to 30%. It means so these two atria help ventricle to fill only 20 to 30%. That's why in books, atria are also called primer pump. It means they're not important so much. Okay, they only boost ventricular filling. Okay, they only help ventricular filling. For example, if I have atrial failure, okay, so I'll not feel signs and symptoms of heart failure during rest. Okay, because I don't need atria. Got it? That this is the importance of this topic. But when I'm exercising, so during exercise, I'll feel the signs and symptoms of heart failure. Got it? This topic is very important because 70 to 80% of ventricles are filling passively. We'll talk about it in next phases. Okay. So now come here to these events. First of all, when these two atria, if I put here a catheter, okay, and sensor catheter, so it sends a bit pressure here, okay, during contraction, and this pressure, if I show you it in a graph, okay, so here during atrial contraction, a small wave is produced. And this small wave is called A wave. This is called A wave. Okay. So during atrial contraction, A wave is produced in atria. First point. The valves which are called AV valves, they're already opened. Next point. 20 to 30% of ventricle filling occur in this phase. Got it? Next, here during contraction of atria, only 7 up to 8 millimeter Eg pressure will be developed. Okay, and during atrial failure, we will not find any signs and symptoms. AV valves are already opened, and as a collectively, this atrial contraction phase takes around 0.1 second. Got it? Now, come here. AC node fires to atria contract. They pump blood to the ventricles. Now, the time will reach that electricity passes or resting membrane potential passes from the AV node to the ventricles. And this AV node is very good, okay, because it takes electricity around 0.1 second, and it will give enough time to the to the atria to empty and pump the blood into the ventricle. Got it? So now, after 0.1 second, resting membrane potential enters to the Purkinje system, and Purkinje system is a very fast system. Now, come here to next phase. Now, a time will reach that ventricle is going to systole. It goes to contraction. Okay. So now, in this phase, listen me carefully. In this phase, when ventricles go to systole or contraction, so these two ventricles produce pressure, and this pressure is more than atrial pressure and less than aortic pressure. It means in these two atria, the pressure was around 7 to 8 millimeter mercury. So here the pressure will be more than 8 millimeter mercury because it contracts, so it generates pressure. And in aorta, the pressure is around 80 millimeter mercury. So the pressure here will be less than 80. So when pressure is less than aorta and more than atria, so this pressure closes these two valves. So due to closing of AV valves, because here pressure is more than atria, so these two valves here the in the left side, the mitral valve closes, and here in the right side tricuspid valve closes. So due to closing of these two valves, a wave will be produced, and this wave causes production of sound, okay, which we can hear it by stethoscope, and this sound is called first heart sound. This is called a first heart sound, which is softer and a bit longer than second heart sound that we will talk about it. Okay, so here in this stage, I'll tell you the name of this stage, don't worry. Here we cannot pump blood from the inside of the heart to the outside because pressure is here in the left side, pressure is less than aorta, in the right side pressure is less than pulmonary artery, and also we cannot receive blood from these two atria. So when I cannot eject blood and also I cannot receive blood, so it means there is no change in volume of left ventricles. So this is called isovolemic. It means no change in volumes. Plus heart is during contracting, but till now the length of sarcomeres are not changed. Okay, so that's why this phase is also called isometric phase, because till now the length is not changed in ventricles. Got it? So sometimes as a collectively we call this phase isovolumetric contraction. It means no change in volume, no change in length, only pressure rises. Okay, so now in this phase, what will occur first in atria? We had a wave here, and this wave was due to contraction of atria. Here, after a wave, you will find a small wave which is called C wave, Now, why is this C wave produced? Got it? Now, listen to me. When these two valves close, okay, so due to closing of these two valves, a backflow of blood occurs, and this backflow of blood causes production of wave and small pressure in the atria, and this wave is called C wave. So come here in a nutshell, in isovolemic contraction phase in atria you will find C wave due to backflow of blood into the atria due to closing of AV valves. Point number two, ventricular systole begins. In this phase, systole of ventricle begins. Point number three, ventricular pressure is more than arterial pressure. Point number four, AV valve closes and causes production of a sound which is called S1 or first heart sound. Point number four or five, ventricular pressure is less than aorta. It's more than atria and less than aorta. No volume change, no size change, and this phase takes around 0.05 seconds. Now a time will reach. Now pressure is during increasing. A time will reach that the ventricle pressure rises, then the arterial, then the aortic pressure. So here pressure in aorta was 80. Now a time will reach that I'll reach that my ventricle reaches to a pressure which is more than 80, which is 81. When I reach to 81, so now these two valves here in the left side, aortic valve, in the right side, pulmonary valve, there is no difference between the cardiac cycle of left side of the heart and right side of the heart. The only difference is in pressure and some small differences. Okay, so now in this phase, in next phase, when left ventricle pressure increases, then the pressure of aorta, okay, when it crosses the pressure of aorta, so now this aortic valve here and pulmonary valve here, it will open, and now heart ejects blood to the systemic circulation. Okay, it pumps blood because valve is opened here, okay, by this pressure. Now this phase is called ventricular ejection phase. It means I'm ejecting now blood to the different systems. Got it? Now come here. This is so easy. In this phase, okay, in ventricular ejection phase, here in atria we had A wave, here A wave due to atrial systole, here C wave due to what? Due to isovolemic contraction phase. Here we will produce a wave that now these two atria act as a reservoir, as a tank. Okay, they fill themselves. Now got it? So to the left atria, blood is coming from the pulmonary circulation. To the right atrium, blood is coming from systemic circulation. And this accumulation of blood causes production of a slow wave which is rising, and this is called V wave. So in atria we will produce V wave in this phase. Here in ventricle, pressure increases more than aortic pressure, plus ejection of blood will be started here. Got it? So in this phase, number one, V wave produces and progression of V wave starts. Number two, ventricular pressure is more than aortic pressure. Number three, rapid ejection occurs. This is very important because when ventricle pumps its blood and it empties its blood into circulation, okay, it pumps all this blood in two phases. Okay, first it pumps a lot of blood rapidly, okay, which is around 70% of blood which is pumped by the heart. For example, this is an example. If my heart ejects 100 ml of blood, so 70 ml will be ejected in this phase, and remaining 30 ml will be ejected in next phase, which is a bit slower than this, and this is called slow ejection phase. So here in this phase, in this rapid ventricular ejection phase, 70% of blood will be ejected. Got it? And this rapid ventricular ejection phase is around 1/3 of all ejection phase of the left ventricle. Got it? Plus left ventricle pressure is more than aorta, and it's around 80 up to 120 millimeter mercury in adult in a physiological state. Okay, aortic pressure. Okay, now aortic pressure is equal to left ventricle. Why? Because now the aortic valve is open. Here in the other side, pulmonary valve is opened. So now there is direct connection between aorta and left ventricle, and here is direct connection between pulmonary artery and right ventricle. So the pressure of left ventricle is equal to the pressure of aorta. For example, if I have 120 millimeter Hg pressure in left ventricle, so the pressure of aorta is also 120 millimeter mercury. Here on the right side, if systolic pressure is around 25 millimeter Hg, so in pulmonary system or pulmonary artery, the pressure is also around 25 millimeter mercury. So it takes around 0.25 up to 0.30 seconds plus the two other phases of ejection also. Okay, so here our aortic and pulmonary valves open. Okay, and opening of the valves do not produce sound. Got it? Now this is slow ejection phase. Only 30% of ejection fraction will be ejected in this phase. Got it? Now a time will reach that now I'm at the end of systole. Okay, I ejected my blood, which was stroke volume. Okay, now I'm entering to the diastole phase, to the repolarization, or to relaxation of the heart. Okay, and this relaxation is now like this. Listen me carefully. Now the left ventricle pressure falls, okay, below the, this the left ventricle falls below the aortic pressure, and it's more than atrial pressure. So it means when this pressure falls below the aortic pressure, so this, because in aorta now pressure is around 80. Okay, here pressure also drops, it's around 80, and here in left ventricle pressure is less than 80, it means around 79. Got it? Plus for example in atria pressure is around 5 to 6 millimeter Hg. So here pressure is more than 5 to 6, so it means the pressure in left ventricle now it's between 6 and between 79. Okay, or it's less than atria and more than aorta, less than aorta and more than atria. So now this valve will be closed. Which valve? The semilunar valve in the left side, aortic valve, in the right side, pulmonary valve. Listen me carefully. In this stage, during ejection phase, okay, when a heart pumps blood, so it causes stretching of aorta also. For example, this is aorta, and aorta is an elastic artery, so it stretches. So when it stretches, okay, in this phase, in this next phase, it recoils back, and when it recoils back, it produces a pressure, and this pressure is called diastolic pressure, because heart is doing diastole, and it produces a pressure by the recoiling of aorta, which is around 80 millimeter Hg. So it does two works. First, it pushes the blood toward the systemic circulation, plus it pushes the blood to the backside, which causes closing of aortic valve, and in the right side by pulmonary system, closing of pulmonary valve, and closing of these two valves produce a sound which is called S2 sound. And S2 sound is, it has a higher pitch than S1 sound, and it's short. Okay, now here is the concept of splitting. Splitting means that first aortic valve closes, then pulmonary valve closes. Okay, and because it's S2 sound, so aortic the aortic valve is called aorta. So the sound which is produced by aortic valve is called A2, and the sound which is produced by pulmonary valve, this is called P2. So between A2 and P2 we have a splitter, we have small phase which is called splitting of S2. And I'm not going to talk about heart sounds in deep details, but we will talk about the heart sounds in future lectures, inshallah. Okay, so now but in a nutshell, these two valves close together, okay, in same time. So now in this phase is called isovolumic relaxation phase. Why it's called isovolumic relaxation? Because here it was isovolumic contraction, heart was during systole, and there was no change in volume and no change in size of the heart. And here heart is during relaxation, so no change in diameters of and or in the length of the myocardium, but there might be a bit change because it's during diastole. But there is no change in volume because this valve is closed. I cannot get volume to the left ventricle, and these valves are closed, and I cannot eject blood from the left ventricle and right ventricle. Got it? So that's why no volume change. It's called isovolumic or isovolumetric relaxation phase in heart is during relaxation. Got it? So now in this phase, what things occurs to atria. Now furthermore, blood is coming to the atria from the pulmonary system and from the systemic circulation. And here we had A wave, C wave, V wave here, and V wave is in progression because now a lot of blood accumulates inside the atria. Okay, here this was V wave progression. Now ventricle pressure is greater than the atria or than the atria pressure, and it's less than aortic or at the right side from pulmonary artery. Okay, when articular pressure is less than atria, I explained it. Now in this phase, these two valves close, which are called semilunar valve, and they produce a sound which is called S2 sound. And I talked about splitting sound, and as a collectively this phase takes 0.05 seconds. Got it? Now diastole continues. Okay, now a time will reach that heart is relaxing, heart is relaxing. A time will reach that pressure drops into in these two ventricles less than atria. Okay, when the pressure drops below the pressure which is in atria, so automatically, because now in atria pressure is high, then the pressure in ventricle, so it causes opening of AV valve in left side mitral valve and right side tricuspid valve. So now a lot of blood enters to the ventricle suddenly and passively. Okay, so now a ventricle during diastole, during relaxation, acts as a reservoir. Got it? So now ventricle is during filling itself, and this phase is called rapid ventricular filling phase. Okay. Now in rapid ventricular filling phase, ventricle pressure is less than atrial pressure. Okay, and also AV valves open. Okay, V wave drops because now when a lot of blood falls into the ventricles, okay, so this curve which was produced by accumulation of blood volume in atria, so this curve also drops. Okay, and also this is a passive, there is no contraction of atria, but ventricle is filling in this time. Got it? Now come here. Now it continues, this relaxation continues a bit more, and now blood comes slowly to the ventricles from the atria slowly, okay, and this stage is called diastasis or slow ventricular filling phase, and this is the longer phase of ventricular relaxation and diastole. Got it? So slow flow occurs, it's around 0.1 second, okay, got it. Now here in this rapid phase plus slow phase, around 70% of blood is pushed from the atria to the ventricles automatically and passively. Got it? That's why when we enter to the next cycle, and again now is unit fires, and the cycle is repeated from the first. Now again atria contracts, so atria now here ventricles are filled more than 70 to 80%. Got it? And it pumps only 20% furthermore, and the cycle continues. So all this cycle causes one heartbeat. Okay, so here we had systole and diastole phases. For example, this phase of ventricle, I'm talking about ventricles. This was diastole, okay, of ventricles. This was systole, this was systole, this was systole, this was diastole, this was diastole, this was diastole. So one diastole, two, three, four. One systole, one, two, three. So in one heartbeat, we have one systole plus one diastole, and all mechanical events in one systole plus one diastole is called one cardiac cycle. And in a cardiac cycle, diastole phase is longer than the systole phase. For example, cardiac cycle time is directly proportional to heart rate. For example, if my heart rate is around 72 beats per minute, okay, so my cardiac cycle time will be around 0.8 second. Okay, for example, now if one heartbeat is 0.1 second, so 0.5 second is made of diastole phase and 0.3 second is made of systole phase. Got it? So this is very important, this passive filling of the ventricles. Now let me show you all these phases in a graphic presentation. Got it? Now let me show you the cardiac cycle in a graphic presentation. If we put a device, a catheter here, so this device will show us some graphic presentation, and I'll explain it here, okay, because in Guyton and Hall we have this is so easy, don't worry. Okay, here this is pressure, okay, from 0 up to 120 millimeter Hg. Got it? Here these are phases. This phase is called atrial contraction phase, which is first phase of cardiac cycle. The isovolemic contraction phase, ejection phase, isovolemic relaxation phase, rapid filling phase, slow filling or diastasis phase, and again atrial contraction phase. Now let me show you the pressures which are developed during this cardiac cycle. First of all, in atria, okay, I'm talking about left atria and left ventricle and aorta, and the cycles and events will be the same as the right side of the heart, only the difference will be the pressure difference. Got it? Now about the atria, here is now this is atrial contraction phase. During atrial contraction phase, a small wave was produced, which is called a wave, and this is around 0. It's around 8 millimeter Hg or mercury. Okay, during isovolemic contraction phase, in this phase, after a wave, a small wave was produced, another small wave which is called C wave. Okay, so here you will find a C wave. I'll go in this one color. This is called C wave. Okay. So now here in these phases, in this rapid ventricular ejection phase, in this phase which mitral valve is closed, in isovolemic relaxation phase, up to rapid ventricular filling phase, in all these phases, mitral valves are closed. Okay. So in these phases, a wave was produced and was in progression, which is called V wave. Okay. So here in ejection phase, you will find a V wave that's in progression. Okay. Here in this isovolemic relaxation phase, you will find a V wave which is in, in progression because blood is accumulating inside the atria. And rapid filling phase. Now in this phase, now here pressure drops. Okay. Here pressure drops. V wave drops. Got it? In rapid ventricular phase, and also in slow ventricular filling phase also this pressure drops. Okay. And again when atria contracts, it produces a pressure. So this curve is called this red curve, this is called atrial pressure curve. Got it? Now about the ventricles. Here in ventricle, here the in ventricle, the pressure is equal to the pressure of atria because there is direct connection between atria and ventricles. Okay. In right side and also in left side. So in left side, beside the A wave, ventricle produces a pressure curve which is equal to the A wave. So this is for example, I'll take a black color. So this is the wave for this is the wave this is the wave of atria. Okay. Of ventricle. So in this here, in isovolemic contraction phase, pressure rises, it increases. Okay. But it's less than 80, it's less than aorta. So here I'm going from this phase from 7 to 8 up to up to 80. Okay. Up to 80. Got it? So this up to 80. Like this, I'll bring it like this, up to like this. Got it? Now this is isovolemic contraction phase. In next phase, in ventricular ejection phase, pressure furthermore increases. It reaches up to 120. So I'm going to 120 like this. Okay. Like this. Got it? Now in this phase, in these two phases, I'm reaching around 120. But now here in isovolemic relaxation phase, the pressure drops below 80. Pressure drops below 80 because the aortic valve closes. Okay. Now here pressure drops below 80. Got it? So now in next phase, which is rapid ventricular filling phase, here the pressure drops below the pressure of atria. It means below the pressure of 7 to 8 millimeter Hg. Got it? And here also pressure furthermore drops. Okay. Here pressure furthermore drops. Okay. And again atria pumps and the pressure of ventricle is equal to the pressure of atria. So this curve, this blue curve, this is called okay, this is drawing. Okay, not like book, but anyway, this is called left ventricular pressure curve. This is called left ventricular pressure curve. Come here to the aorta. Now here and in atrial contraction phase, here because aortic valve is closed and also pulmonary valve is closed. Okay, both valves are closed. So here the pressure in aorta is around 80 because less pressure, which is in our it's around 80 millimeter Hg during diastole in normal person. Okay, so here in atrial contraction phase, there is no change in aorta. There is no change in aortic pressure. In this phase, which is isovolemic contraction phase, also there is our aortic valve is closed. So there's also no change in isovolume contraction. There is also no change in curve. Okay, but here in this phase, when ventricles contract, okay, so the pressure is equal to the pressure of aorta because there is direct connection. So the pressure of aorta rises from 80 to 120 millimeter Hg. Come here, come here. In these two phases, pressure rises. Okay, but in this phase, in isovolemic relaxation phase, the pressure of aorta drops. Okay, near the 80. When the pressure here it drops. Okay, so here it produces here is a bit small new curve will be produced here, and this is called incisora. This is called incisora. I don't know spelling of it, but this is called incisora. Why is this produced? Because in this stage, in an isovalent relaxation phase, when a aortic valve closes, it causes a bulging, a backflow of blood to this side and also to this side by the recoiling of aorta, and it produces a small ejection, a small wave-like pressure, which is called incisora, and this is due to closing of these valves. Now, here now in isovolemic relaxation phase, pressure reaches to 80. In this stage, in rapid ventricular phase, now this valve is closed completely, so there is no change in aortic valves, so curve remains normal. Okay, also here is no change in this slow ventricular filling phase until here, and also curves, but it drops a bit because aorta recoils. Okay, and again when here up to here it's equal, and again during isovolemic contraction phase, in ejection phase it rises. So this green curve is called aortic pressure curve. This was atrial pressure curve, this is aortic pressure curve, and this blue one was left ventricular pressure curve. Got it? Now come here, come here, come here, come here, come here to the volume of left ventricle. Okay, so now here in this direction, in this axis, okay, this is this, I think, why this x. Okay, in this axis here we have mLs. Okay, this is 50 ml, this is 90 ml, this is 130 ml. So during systole heart pumps and ejects a stroke volume which is around 70 ml, but amount of blood always and always remains here inside the ventricles, which are called end systolic volume, and normally it's equal to 50 ml. Got it? So now here, come here, in this stage 70% of 70 up to 80% of ventricles was filled passively, and when atria contract, okay, this in left side it fills left ventricle furthermore. Okay, so for example, in this stage the blood is around 80 to 90 ml. Okay, and furthermore 20 to 30 ml will be pumped from the atria to the ventricle. So in this stage, from 90 ml, listen me carefully, from 90 ml I'll reach to 120 ml. Okay, here in this phase, in isovolemic contraction phase, there is no change in volume, so the graph remains in plateau or straight. Here I eject blood from the heart, so in both phases here the slow and rapid, in rapid and slow, in both phases, I eject blood from the heart. So the blood volume of the left ventricle drops. Okay, I lose a lot of blood. Okay, now in these two phases, I'll eject around 70 ml blood from the ventricle. I'm talking about left ventricle, and 50 ml remains with us as a in systolic volume. Okay, so I'll reach here up to 50 ml. Now in this phase, which is isovolemic relaxation phase, no change in volume. Okay, so no change in curve of left ventricle volume. Got it? Now here, come here, rapid ventricular filling occur. Okay, so when rapid ventricular filling occur, I'm going again from 50 ml up to 70 or 80 ml, and here again slow filling occur, and I reach from 7 here from 50 to 70 80, and here from 70 80 up to 90, and I'll again reach here up to 90 ml, and again atria contracts and boost our left ventricle volume furthermore. Got it? So this was left ventricular volume curve. Got it? Now come here to ECG. This is easy. We will talk about ECG in upcoming video lectures in deep details. But anyway, listen be careful. This is easy. When AC node fires, okay. So first AC node fires, okay. It means before contraction, electrical events occur. And in ECG, we have do you know about the ECG? Come here. We have, for example, P wave, Q, or S, T. Okay, this P wave is due to atrial contraction or atrial depolarization. This QRS is due to ventricular contraction. This PR inter this one, this PR segment, this is P, this is R. This PR segment is due to AV node depolarization. This ST, this is QRS. This ST segment is due to ventricular depolarization. This is due to plateau phase, and this T wave is due to ventricular depolarization. Okay, got it. Now first of all, this P wave occurs, and then it causes contraction of atria. So here in graph, don't think much more about ECG. I'll teach it in full details. Don't worry, okay? But anyway, here first of all in graph, P wave occurs, and then atrial contraction comes. Okay, and then now electricity is with AV node, and then first QRS complex occur, and then contraction of ventricles, or this isovolemic contraction plus these ejection phase, that depolarization or contraction of ventricles occurs. So this about phi QRS T. Don't think much about ECG. Here in isovolemic contraction phase, we had a sound which is called S1 sound. So in phonography, here in atrial contraction, it's not in atrial contraction, it's not in atrial contraction. In isovolemic contraction, in this phase, we had a sound which is called S1 sound. So you will hear a sound in stethoscope which is called lobe, and the next sound is called dub lub dub lub dub lub dub lub dub. This is first heart sound, this is second. So first heart sound plus second heart sound, as a collectively it's one heartbeat or one systole plus diastole. Here come here to isovolemic relaxation phase. In this phase is two heart sound occurs. Okay, so this is a sound which is called S2, this is S1. Sometimes, listen me carefully, sometimes due to rapid ventricular filling, specifically during exercise in athletes, okay, due to rapid ventricular filling to the ventricles, a sound will be produced which is called S3 sound. This S3 sound can be pathological and can be physiological. So this S3 sound is produced during rapid filling phase, during rapid filling phase. Okay, and sometime here in phase 1, here an atrial contraction phase due to pushing of blood from the atria to the ventricles through a narrow structure. For example, here if we have mitral stenosis, so it produces a sound which is called S4 sound, and S4 sound is always and always a pathological sound. Got it? So this was about phonography, this was about ECG, this was about left ventricular volume, this was atrial pressure curve, this was left ventricular pressure curve, and this was aortic pressure curve. Now we will talk about some important topics in about cardiac work and so on.